least mean square filter or Wiener filter. So these filters are used for image restoration. So degradation function H with noise and restoration filter given with W, Wiener filter, and output is F cap. Input is F. Here the output is G of X comma Y, which is degraded image. G is equal to F into F convolution H plus N. F cap is equal to W convolution G. So frequency domain representation is G is equal to F into H plus N. F cap is equal to W into capital G. Wiener filter. Or least mean square filter. Least mean square filter. In least mean square filter, we minimize the error function. E is equal to F cap minus F. E square is equal to F cap minus F whole square. So MSE, mean square error, is equal to expectation of E square, that is equal to expectation of F minus F cap whole square. That is equal, that implies assume noise and image are uncorrelated. That means expectation of error and degraded image is equal to 0. So E is equal to F cap minus F into G is equal to 0. That implies E of Fg is equal to E of F cap G. We already know F cap means W convolution into G. W convolution G into G. That implies E of W convolution G into G star. Now expand the convolution function. E is equal E of sigma into sigma W of K1 comma K2 G of X minus K1 comma Y minus K2 into G star. Here W is constant, so put it out. W of K1 comma K2. E of sigma into sigma G into G star. Here both functions are same. So expectation of both functions means it is autocorrelation. RGG. Here RFG, cross correlation function. RFG is equal to W into RGG. That implies Wiener filter W is equal to RFG by RGG. Now we have to calculate RFG. That is equal to expectation of FG. That is equal to F. Already we know G is equal to H in H convolution F plus N. Substitute this here. H star of F plus N. E is equal to F into H convolution F plus F into N. Expectation of F into H convolution of H plus E into F is equal to 0 because function and noise must be uncorrelated. For uncorrelated functions, expectation is equal to 0. So that is equal to E into F H convolution of F. Now expand the convolution. F into sigma H of K1 comma K2 F of x minus K1 comma y minus K2. That implies here H is constant. Put it outside. H of K1 comma K2. E of sigma F x comma y F of x minus K1 y minus K2. That means H of K1 comma K2 expectation of same functions. So it represented as autocorrelation function F. So RFG is equal to H of K1 comma K2 RF. Now similarly calculate RGG. That is equal to expectation of G into G. That means G of E of H convolution of F into H star of convolution of F plus N. It means E is called E of H convolution F H convolution of F plus 2 into H convolution of F into N plus N into N. Next expectation of H convolution of F H convolution of F plus expectation of H convolution of F into N plus expectation of N into N. Expectation of N into N is written as autocorrelation. Here F and N are uncorrelated, so this equation becomes 0. This equation expand convolution. E sigma H K1 comma K2 into F. Again sigma H K1 comma K2 into F plus 0 plus RNN. Here H is constant, so put it outside. H into H. Expectation of sigma F plus RNN. H into H. H square expectation of F into F. So it is autocorrelation function RFF plus RNN. Therefore, W is equal to RFG by RGG, that is equal to H into RFF by H square RFF plus RNN. This is time domain representation. So frequency domain means autocorrelation function is represented in power spectral density. So capital H into power spectral density S of u comma v plus H square of u comma v into SF u comma v plus Sn u comma v. Now restored image f cap of u comma v is equal to W of u comma v into G of u comma v. Substitute this W here. H of u comma v SF plus by H square of u comma v into SF u comma v plus Sn u comma v into G of u comma v. Now so common SF. Sn by SF. This is the final restored image using Wiener filter.